In this video we're going to be looking at differentiating the trig functions. Now we need to know how to differentiate sine, cos and tan. We also need to know what happens when we differentiate their reciprocal functions. And we're going to start off by doing a little bit of investigation and then we're going to just try and use the rules as given. So here's the sine graph. We're going to look at what happens when we differentiate the sine graph by looking at the gradients of the curve. So we can already see that at pi over 2 we're going to have a gradient there of 0, and at negative pi over 2 we also have a gradient of 0. So in green I'm going to try and plot the graph that I would get if I was to differentiate sine. So at those particular points we know the gradient is going to be 0. Now it might be hard to see this next one because the scales aren't equal. This scale here is a scale of 1 and this scale across here is pi over 2. But at the point where it crosses the origin, the sine graph actually has a gradient of 1. So I'm going to go ahead and plot that point there. And at pi and negative pi, these gradients here would be negative 1. So I'm going to go ahead and plot those points at negative 1. Now the next thing I'm going to look at is what's actually happening to the gradient of the curve between 0 and pi over 2. And as you can see, the gradient is starting to flatten out here until it gets up here where it's perfectly horizontal. So what we're going to get is kind of a curve coming down like this. And then on the other side, so this is between pi over 2 and pi, the gradient goes from being flat and it starts increasing in magnitude until it gets to that point there, which has a gradient of -1. So we're going to again try and curve this one round the other way. And if I go ahead and do that to the other side, we get something that looks a bit like this. And what we've actually drawn there is the cos graph. So if we differentiate sine, we get cosine. Well, now let's have a look at what happens if we differentiate the cosine function. We're going to try and do this in the same way. So again, here at 0, we've got a gradient of 0. At pi and negative pi, we're going to have gradients of 0. So let's mark those 3 points up. Now at negative pi over 2, this is where the gradient would be 1. And at pi over 2, this is where the gradient would be -1. And again, the same type of idea occurs between these key points. So from 0 to pi over 2, the gradient is going to increase in magnitude and head towards -1. And then from negative pi over 2 up to 1, it is again decreasing from a gradient of 1 all the way down until it gets to the top where it has a gradient of 0. So this is going to come down like this, and then it's going to keep coming down and flatten like that. And on the other side, if I was to look at them, it would increase there, and this one would come down as well. And what we have there is the sine graph that has been reflected in the x-axis. If we have differentiated that cosine function, we've actually ended up with the negative sine graph. It's also a cos graph that has been translated, but the best way to look at this, for reasons we'll see in a second, is that if we differentiate the cosine function, we get the negative sine graph. So sine went to cos, cos has gone to negative sine, and if we continue doing this type of idea by looking at the gradients, we'd actually get this what we call wheel of differentiation. So sine has gone to cosine, cosine goes to negative sine, negative sine would therefore go to negative cosine, and negative cosine goes all the way back to sine. So that's why you can understand that it's called the wheel of differentiation. We've also got the more technical way of writing it here at the bottom. Now the third one of these trig differentiations, differentiating tan, is a graph that you would never have tried to guess in your life. Okay, so just try and learn this extra one over here on the right hand side. If we differentiate tan, we get sec squared. It's a bit more of an awkward one to try and remember. If you want to plot the graphs yourself and have a look at what happens, just use Desmos. It's quite easy to use. But those are the three main trig differentiations that we need to know. From there, we can use chain rule to try and differentiate any more complex ones. So if we want to differentiate cosec, we could write cosec as sine x in brackets to the power of -1 and then apply the chain rule from there. And it's the same as if we want to do sec or cot. Now the other thing we're going to do to prove these even further is we're going to look at what happens if we were to differentiate sine by first principles. So hopefully you can remember how to do this from previous. We start off by writing y equals sine x. That is the thing we're going to differentiate. So if we differentiate this function, we say we're going to limit this h as it gets closer to 0, and it starts off by saying it's sine of x plus a tiny adjustment minus the actual function all over, and it's really over the difference, which is x plus h minus x, which is always going to leave us with that h at the bottom. So this is a familiar topic. This is a addition rule. So hopefully we can remember that if we expand the brackets of sine x plus h, we get, let me get the limit put in first, we get sine x cos h plus sine h cos x minus sine x all over, and I'm going to write h. Now depending on when you're watching this video, we've just got to be careful with this notation here. If you're watching this in year 13 and you've learned about hyperbolic functions, this does not say cosh and this does not say sine, that says cos h and sine h. So just be careful for this question. If you haven't done that yet, that'll mean absolutely nothing to you at the moment. Now what we're going to do now then is, in order to try and show what we need to do here, we're actually going to do a little bit of factorising on that numerator. We're going to factorise these two circle terms here, and that's going to get me the limit as h tends to 0 of sine x and then cos of h minus 1 plus, and on the other part we're still going to have that sine h cos x all over h. And now we need to try and work out what's actually happening. So now we're going to maybe take into account that limiting factor. In fact, maybe what I'm going to do just before I do that is I'm going to write one more line in here that looks very similar, but I'm actually going to split this fraction into two parts. And I'm going to write it almost exactly the same, but very, very slightly differently. So I'm going to write it like this, over h, and on this side I'm going to write it as sine h over h times by cos x. So the reason I'm writing it like this is because these h's in brackets on the left hand side, this one here anyway, and this part here, we can try to work out what's actually going to happen to that as h tends to 0. So the first thing we can look at is this particular bracket here. Okay, if h is tending to 0, that's basically getting closer and closer and closer to cos of 0. And cos of 0 is going to get us to 1. So that this bracket here essentially is going to become 0. If this bracket is 0, that means this entire section over here is going to be 0 as well. It is going to completely disappear as h gets closer to 0. What I'll do to show that then is I'm going to put like a strike through it and say this is going to tend to 0 as h gets closer to 0. Now on the other side, we now need to look at this section here. So as h gets closer and closer to 0, sine h also gets closer and closer to 0. Sine of 0 is 0, so as h gets closer and closer to 0, that value there is going to become increasingly small. But it's happening at the same time as h itself is also becoming equally small. So these two things are both going to be incredibly small, and they're going to start getting closer and closer to each other. Therefore, this part here is essentially going to equal the value of 1. So again, I'm going to put a rule through that and say that this part is going to get closer to 1. And what we're now left with then is 0 add 1 lot of cos x. So therefore, let's put this part back in. If we differentiate sine x, we're going to end up with cos x. Now, we may need to prove for first principles differentiating cos to get sine, but I think that will be on a worksheet that we're going to be looking at soon. So now we're going to try and differentiate some of these more complex trig functions. Now I'm going to do the first one by chain rule, and then we'll try and break down what's happened, and it will probably apply for all the other ones as well. So for the first one, I'm going to make this angle equal to u. So I'm going to say let u equal 5x. So that means du by dx, if we differentiate 5x, is just 5. So y is now equal to sine of u, dy by du. So we said if we differentiate sine of x, we got cos x. So if we differentiate sine u, we get cos u. So if we multiply those two things together to get dy dx, we're going to get 5 cos u, which equals 5 cos 5x. So if we now try and work out how we could have got that from just the original function, there's about 3 steps that we need to do. First of all, we take the trig thing and we can apply either that wheel of differentiation, or if it's tan, we can just write it as sec squared. So we're going to change this sine to cos. The angle never changes. So that angle of 5x over here has stayed in my answer. And at the beginning, we've multiplied it by the derivative of the actual angle. So there's always kind of like 3 steps here that we could do that would entirely skip out this entire chain rule. It's change the trig, keep the angle the same, multiply it by the angle's derivative. So if we now try and do the second one here by that logic, we can say dy by dx is going to equal, so cos becomes negative sine, the angle stays the same, and we times this by the derivative of the angle. 3x derives to just 3. So my answer for that one would be minus 3 sine 3x. For the next one, we'll do exactly the same. Tan becomes sec squared. The angle stays the same. And then we times it by the angle when it has been differentiated. Now for these ones with powers, don't forget that sine squared x actually just means sine x all squared. So we can do differentiate this one again by using what we know about the chain rule. So this is going to start off by saying keeping that bracket the same, decrease the power, bring the old power down. But then we also have to times this by the bracket differentiated. So sine becomes cos x. So if I write that a little bit nicer, it would just be 2 sine x cos x. Same with the next one. I'm going to start off by maybe writing it as tan x all cubed. So dy dx is going to equal the bracket, bring the old power down, decrease it by 1, and times it by the bracket differentiated, which is sec squared x. And if I want to put it back into maybe nicer notation, we could write this as 3 tan squared x sec squared x. And for the last one here, same idea. We're going to make dy dx equals, we're going to keep the bracket the same, but decrease the power and bring the old power down, times by this bracket differentiated, so 1 is just going to disappear, and then cos of 8x, if we try and differentiate that, cos becomes negative sine, the angle stays the same, and we also have to times that by the derivative of the angle, which was 8. And again, I could maybe write this one a little bit nicer as minus 40 sine 8x times by 1 plus cos 8x to the power 4. So question 3 says use the chain rule to show that if we differentiate cosec, we get negative cosec cot x. So if I was to write first of all y equals cosec x, I could now write this as sine x to the power of negative 1. That means dy dx, the thing we're trying to work out, would become minus sine x to the minus 2, so that's me bringing the old power down and decreasing the current power by 1. Also times this by the bracket differentiated. Sine x becomes cos x. Now if I write this in a nicer way, we can see that we're going to have a numerator of minus cos x, and at the bottom we've got sine x squared. So I'm going to write this as minus cos x at the top, and at the bottom I'm actually just going to write it as sine x times by sine x, because now what hopefully we can see is we've got the negative that we need in the question. There's a cot x in what I need, and I know cot x is the reciprocal of tan. Tan is sine over cos, so cot is cos over sine. So that means I've used this negative, this cos, and this sine, and I'm left with 1 sine as a denominator, and 1 over sine is cosec. So I might want to write this in one extra line just to show that I actually know what's going on here. I'm going to write it as minus cos over sine x times by 1 over sine x, and then from there I should have no problem in writing it as negative cosec x cot x. And the next part says hence find out what would happen if the angle changes first of all. So let's actually put this into the previous question and see how it changes. If we've now got cosec of 3x, that means we've got sine of 3x to the minus 1. So then when we differentiate this, The first thing is the 3 would stay inside the bracket, but then when we differentiate the bracket, this would now become 3 cos 3x. So that means I need a 3 here and here, and these would also become 3's. I could put the 3 there and put the 3's here. So it's going to be minus 3 cosec 3x cot 3x. So my answer from A is going to equal, dy dx equals minus 3 cosec 3x cot 3x. For the next one it says what would happen if you differentiate. Let me write this as cosec of x cubed. Well, that means we're going to get 3 lots of cosec x squared. It's decreasing the power, bringing the whole power down, times this by the differential of the bracket. And we know if we differentiate cosec, we get minus cosec cot x. Minus cosec cot x in here. And we could multiply that out to make it a little bit nicer. It's going to get us minus 3 cosec cubed x cot x. And now that we know how to differentiate all these trig functions, we could get the same types of question that we would get in year 12, now just with a trig function attached. So a basic question would be find the gradient of a curve that now involves a trig function. So we want to differentiate 3 cos 2x plus x. And don't forget, this is the type of question that you could easily check on your calculator using the differentiation button. So if we differentiate this, first of all we can see this cos, that's going to become a minus sine. The angle stays the same. And we need to times this 3 at the front by what happens when we differentiate the angle. That's going to get us a 2 times by that 3, so it's going to be minus 6 plus 1. When x equals pi over 12, dy dx becomes minus 6 sine of 2 lots of pi over 12, which is actually just pi over 6 plus 1. So sine of pi over 6 is a half, so this is really saying minus 6 times by a half plus 1, which is minus 3 plus 1, which gets us an answer of negative 2. And then for the final example, again we've got a function to differentiate that involves trig, and this one then says find the x values of the 2 stationary points in the interval from 0 to 2 pi and determine the nature of these points. So we need to differentiate it and then get a second differential to work out if they're going to be maximum or minimums. So let's start off by doing maybe both the differentiation that we need at the same time. So let's write out y equals x minus 2 sine x. So if we differentiate the first time, we're going to get 1. So this is a negative sine. Negative sine becomes negative cosine. The angle stays the same. And if we differentiate the angle in this case and times it by the coefficient, it's still going to be 2. And then when we differentiate this, that 1 is going to disappear. Negative cosine just becomes sine. And we're going to end up with 2 sine x. So we need to find the x values of the 2 stationary points. So let's write stationary points when y dash equals 0. So that means 1 minus 2 cos x equals 0. And now we're just into some rearranging. That means 2 cos x equals 1. Cos x is going to equal a half. And that means x equals pi over 3. And don't forget, if we want to try and get any other ones of a cosine function, we can do 2 pi take away this value, which is going to get me 5 pi over 3, which looks good because it says 2 stationary points and I've got 2 answers. It doesn't say find the coordinates, we're fine. We just need to find the x values, so we've done that. What we do need to do though is determine the nature of these points. So when x equals pi over 3, y double dash is now going to equal 2 sine of pi over 3. Let's have a look at what happens when we do 2 sine pi over 3. We get root 3. And when x equals 5 pi over 3, 2 sine 5 pi over 3, we get negative root 3. And then if we want to maybe write a conclusion here, we can then say when x equals pi over 3, we get a positive number that is bigger than 0. Therefore this one's going to be the min. This one at the bottom is less than 0. Therefore it's going to be the maximum. So we've got a minimum when x is pi over 3. We've got a maximum when x is 5 pi over 3. And just to prove that one, it's a lovely graph. And we can see, I have to get rid of some of this writing, but we can see here that when x is pi over 3, there's our minimum, and when x is 5 pi over 3, there's our maximum.